Hey everyone, I thought I'd do this as a follow-up to my Life on Mars video to give some thoughts as to how we could go about colonizing the red planet. Now, first thing is we need a place to live, and on the surface this is a problem for two main reasons. One is the weak magnetic field of Mars means the surface is bombarded with harmful radiation. Second, the topsoil is between 1 and 0.5% perchlorates by weight. While any astronauts would have to wear a sealed spacesuit when outside, they would end up tracking the perchlorates into their habitat module. Since Martian dust is so fine, the people inside would end up inhaling some of the perchlorates, which would lead to respiratory problems. One way to kill two birds with one stone is to have the habitat modules in lava tubes. Here, the overlying rock would certainly protect the astronauts from the harmful radiation. Since the production of perchlorates seems to be photochemical, the lava tubes should, in principle, be protected from them as well. However, the dust storms which cover Mars once every few years could blow some of the perchlorates into the tubes. Exactly how soil perchlorate levels in the lava tubes compare to those on the surface isn't yet known. A mission to explore a lava tube is in the works, but no formal blueprint for a probe has yet been drawn up. If it does turn out that the lava tubes have much lower perchlorate levels than the surface, it would make them an even more ideal site for a habitat module. The astronauts would get perchlorates on their suits when exploring the surface, but they could have an air hose by the mouth of the tube to blow off the perchlorates far from the habitat module. The perchlorate levels would build up near the mouth of the tube, but they would be blown away when the aforementioned dust storms occurred. Getting a manned mission to Mars would also be quite difficult. For one, the voyage would take most modern craft a year to get there. It would take a spacecraft much larger than the one who took men to the moon because it would have to carry so much more supplies. Not to mention, such an odyssey could cause the astronauts to go stir crazy. A staple way to get around this in sci-fi is to put the astronauts in suspended animation, also often referred to as cryostasis. At the current day, we're a long way off from being able to put people in suspended animation, and by suspended animation, I mean their metabolism halts. But one thing we can do with modern technology is put people in an artificial coma for the voyage. This would also mean the whole habitat module wouldn't have to be shielded, which would cut down on weight. This is of course a risky strategy, and the astronauts might not wake up upon arrival. However, even if the crew died, the mission wouldn't count as a total failure. While the deaths of the explorers would certainly be unfortunate, they would be carrying surface landers, provisions, exploration equipment, and possibly habitat modules. Since these would already be in orbit around Mars, a later mission, once inducing artificial comas is more reliable, wouldn't have to carry as much supplies, since they could use the supplies from the failed attempt. In the meantime, the rovers, orbiters, balloons, etc. that they brought with could be remotely operated from Earth. The first missions wouldn't be aimed at staying on Mars, and instead the astronauts would explore the surface for a few months and return to Earth. When humans landed on the moon, the lander had to have enough fuel to slow it down to land and to lift it off the ground into orbit. Because of this, the lander had to have two stages, each with its own rocket motor. One was to land, and the other was an orbiter that separated upon takeoff. As a side note, a pet peeve of mine is when the moon landing sites is depicted in present or future scenarios with the whole unit present, when the top portion would have taken off at the end of the mission. However, since Mars has an atmosphere, this could be used to slow down the lander as it nears the surface. The landing craft would also deploy parachutes to slow itself down upon final approach, but it would still be falling pretty fast. So, a Martian lander would have to expend some fuel to brake for landing, but this would be nowhere near the quantity used by the lunar lander. Now, you might think it would also have to take the fuel for taking off with it to the surface, adding weight, but this isn't necessarily the case. If it lands near a glacier, i.e. a source of water, the molecules could be split into oxygen and hydrogen via electrolysis. The craft could in principle use hydrogen and oxygen as a fuel source, but there are some downsides to this. For one, a hydrogen tank has to be 10% of the weight of its contents, which would add a lot of takeoff weight. What the landing craft could do instead is react the hydrogen with carbon dioxide in the surrounding atmosphere to produce kerosene via Fischer-Tropsch type synthesis reactions. While not as energy dense as hydrogen, and by energy dense I mean joules per kilo combusted, a kerosene tank usually only has to be 1% of the weight of its contents. So, while the astronauts are out exploring, the lander can use solar power to produce its own fuel from local materials. Because of this, only the fuel to break the lander on final approach has to be brought with it from Earth, sparing the interplanetary mothership a huge weight penalty. For the first missions, the astronauts would bring their own food, but once habitat modules were delivered, they could start growing their own, or farming, on Mars. The greenhouses and habitat modules would be in separate pressurized environments. Now, you might think that since plants uptake carbon dioxide and water and release oxygen, you could just grow them in pressurized Martian air, right? Well, not quite, since plants need oxygen. Yes, they do make it by photosynthesis, but their non-photosynthesizing cells also depend on cellular respiration, i.e. oxygen, to power their metabolism. So, while plants can produce their own oxygen, were you to suddenly remove all the oxygen from a chamber a plant was growing in, it would die before it could produce enough oxygen to support its metabolic needs. However, being sessile organisms, the oxygen demand per kilo of plants will be much lower than ours. Usually, plants will start to suffer from hypoxia at oxygen partial pressures between 0.05 and 0.01 atmospheres. In terms of the total atmospheric pressures, plants start to suffer from deleterious impacts below 0.2 atmospheres. So, if we were to set up a greenhouse on Mars, we'd start by raising the internal pressure to 0.15 atmospheres with pressurized Martian air and add 0.05 atmospheres of oxygen. You might think we'd bring plants who need the least oxygen to survive, but the reason these have lower oxygen requirements is because they have a slower metabolism. This will correspond to a lower growth rate, making less than ideal for farming. Also, at night, the plants won't be producing oxygen, but will be respiring faster, causing the oxygen levels to drop. So, to compromise structural rigidness, which nominally corresponds to weight, and the plant well-being, we probably want to keep the partial pressure of oxygen at the upper limit for plant hypoxia. One thing to note is that any pressurized air containment structure will experience gas loss to the surrounding environment. But since the plants will be using the gases in the atmosphere, this leakage can be used to recycle the Martian gas, so the plants never run out of airborne nutrients. Also, since the structure itself doesn't have to be as leak resistant, it can be less structurally sound, and thus lighter, saving mass for the trip to Mars. Since 1/4 of the molecules are oxygen, so long as the air loss rate doesn't go above 4 times the rate that the plants can produce oxygen, the plants won't suffer from hypoxia. The water would also be collected from the Martian air via a condenser in a pressurized chamber to water the plants. Of course, plants need more than carbon dioxide and water and require other elements as well. These can be obtained from the excrement of the astronauts. It has also been shown that plants can grow in Martian soil once the perchlorates are washed out. But let's say we want to terraform Mars instead of living in a habitat module. How could we go about doing that? Well, first we have to give Mars a breathable atmosphere. In order to have that, we have to put enough oxygen in it. Elemental oxygen isn't hard to come across on Mars, since, after silica, it's the most abundant element in the Martian crust. So, we could quote-unquote bake it out of Martian rocks and release it into the atmosphere as diatomic oxygen. In order to be able to support human life, the partial pressure of oxygen would have to be about 0.11 atmospheres. On Earth at sea level, the partial pressure of oxygen is 0.21 atmospheres. The average pressure of the Martian surface is roughly 0.006 atmospheres. This means that if we go with the sea level partial pressure of oxygen, we'd increase the atmospheric pressure at least 70-fold. But remember that since we're engineering an atmosphere, we aren't stuck with the constraints we have here on Earth. Even though we can breathe perfectly fine at sea level, there are areas like high mountains largely inaccessible to us because there just isn't enough oxygen up there. So, when we're engineering a Martian atmosphere, would we want to make it so we can breathe on top of the highest point, i.e. Olympus Mons? Well, to figure this out, let's look at some basic principles of atmospheric science. As the altitude increases, the air pressure also decreases. The equation that determines the pressure at a given altitude is the pressure at the surface, or P0, multiplied by E to the altitude divided by the scale height, or h. On Mars, the scale height is 11.1 kilometers, and on Earth it's 8.5. The equation for the scale height is equal to the Boltzmann constant, or K, multiplied by the temperature, divided by the product of the average molecular mass of the air and the acceleration due to gravity. The average temperature of the Martian surface is 210 degrees Kelvin, but if we were to terraform it, we'd want to make the average temperature comparable to Earth, i.e. 288 degrees Kelvin. Furthermore, since the Martian atmosphere is 95% carbon dioxide, the average molecular weight is 44, while that of oxygen is 32. With the temperature of the terraformed Martian atmosphere being 37% greater and the molecular weight being 27% lower than that of the current atmosphere, the scale height would be 88% greater than what it is now, or 20.9 kilometers. Let's say we want to make the partial pressure of oxygen at the summit of Olympus Mons the same as that of the Earth at sea level. How high would the oxygen levels be further down? Well, Mars doesn't have a sea level, so we can instead use the average altitude of the surface, also known as datum. The summit of Olympus Mons is 21.3 kilometers above the datum, so if we crunch the numbers with the pressure-altitude equation, the partial pressure of oxygen at datum would be 0.58 atmospheres. Conversely, the lowest point on Mars, which lies in the Hellas Planitia crater, is 7.15 kilometers below datum. So, the partial pressure of oxygen down there would be 0.82 atmospheres. Humans will start to suffer from oxygen toxicity at a partial pressure of 1.4 atmospheres. As such, if we made it so the summit of Olympus Mons had the same atmospheric oxygen levels as Earth at sea level, colonists wouldn't suffer from oxygen toxicity. However, at oxygen concentrations this high, fire becomes a much bigger problem, and we'd have to be pretty careful with any combustible materials. But let's say instead we give Mars enough oxygen that the partial pressure of oxygen at the summit of Olympus Mons is just enough to sustain humans indefinitely. The partial pressure of oxygen at datum would be 0.3 atmospheres, and in the Hellas Planitia it would be 0.42 atmospheres. In my opinion, this would be the best compromise between maximizing the total habitability while minimizing any fire hazards. But what about the other gases in the Martian atmosphere? Well, as previously stated, the Martian atmosphere is almost entirely carbon dioxide, and the pressure is on average 600 pascals. Carbon dioxide will become toxic at a partial pressure of 1200 pascals. The partial pressure of carbon dioxide in the Hellas Planitia would be 845 pascals in the terraformed atmosphere, so we wouldn't have to remove any carbon dioxide from it. If we want the overall pressure of a terraformed Martian atmosphere to be comparable to Earth and not have to worry about increased fire hazards, we'd have to fill it with other, preferably inert gases. Earth's atmosphere is 75% nitrogen and 3% argon. So, could we put these in the Martian atmosphere? Well, unlike oxygen, the elemental forms of these are pretty rare in the Martian crust. So, if we want to have these gases in the Martian atmosphere, we'd have to transport them from somewhere else. The atmospheric pressure of Earth at sea level is 1,325 pascals, and 1 pascal is 1 newton per square meter. Since the surface pressure is essentially the weight of all the air pushing down on the ground, to know how much mass is above 1 square meter, we divide the pressure by the acceleration due to gravity. On Mars, this is 3.72 meters per second squared, and we get 27.2 tons. The total surface area of Mars is 1.44 times 10 to the 8th square kilometers, or 1.44 times 10 to the 14th square meters. If we multiply that by 27.2 tons per square meter, we'd get a total mass of the terraformed Martian atmosphere of 3.92 quadrillion tons. Since 78% of that is gas we'd bring over from elsewhere, maybe Saturn's moon Titan, we'd have to transport 3.06 quadrillion tons of nitrogen to Mars. For some perspective, about 11 billion tons of goods are shipped across Earth's oceans every year. I mean, sure, we definitely have better technology when colonizing Mars than we do now, but when we move materials across an ocean, we don't have to escape a gravity well. Given the enormity of this task that would only add a bit more familiarity to a terraformed Martian atmosphere, I'd argue we'd omit filling it with nitrogen when colonizing Mars. Although, having a thinner atmosphere will pose some challenges. For one, the boiling temperature of water will be around 61 degrees Celsius. This is below both our own body temperatures and the highest recorded ambient temperature, which was around 55 degrees. So, we're safe in that we wouldn't have to worry about water suddenly boiling on us. However, the evaporation rates will be much faster, meaning bodies of water will more readily dry up, and we'll have to more frequently irrigate our crops. But, how would aircraft fly in a thinner atmosphere? Well, airfoil surfaces like wings would generate less lift when moving at a given speed. However, with the surface gravity of Mars being 34% of the Earth, they wouldn't have to generate as much lift to get the entire craft airborne. The equation for the lift a wing provides is the product of the lift coefficient, 0.5, the area of the wing, the atmospheric density, and the velocity squared. So, if the terraformed Martian atmosphere had a surface density between 30% and 22% that of the Earth at sea level, an airplane would have to be going 6.5% and 24% faster respectively than it would on Earth to get off the ground. I.e., the takeoff speeds of Martian airplanes wouldn't be that much greater than those on Earth. Also, since the atmosphere is thinner, Martian airplanes could fly much faster at low altitudes than they could on Earth. Furthermore, since Martian gravity is much lower, the rate at which the atmospheric density decreases with altitude will be less, so the airplanes could fly much higher than here on Earth. Since turboprop planes are limited by how much air their propellers can bite into, we'd probably only be using jets on Mars. And, since the orbital velocity of Mars is less than the Earth, single-stage to orbit craft would be much more viable. These could use a jet engine to get to their flight ceiling, and then use a rocket to boost into orbit. To raise the temperature of Mars, some have argued that we should slam asteroids into it, but this can have some serious downsides. For one, there are many caustic chemicals, such as the aforementioned perchlorates, in the soil, and these would be released into the atmosphere upon impact. Second, while it would initially heat the planet, the dust thrown into the atmosphere can block out the sunlight and cause a nuclear winter, which would cool it, i.e., having the opposite of the desired effect. One possible workaround might be to blow up the asteroid shortly before impact, increasing the total area which will be in contact with the air and ensuring that most of it burns in the atmosphere, and thus heats it. Although, there will be a large degree of variation in the size of the fragments, so larger fragments will likely hit the surface with a lot of force. Going back to the raw numbers, what is the total quantity of asteroid material needed to sufficiently heat the Martian atmosphere? Let's say we gave Mars an atmosphere with a surface pressure 25% of that of the Earth at sea level, and, to make it comparable to Earth, we'd have to raise the temperature by 78 degrees Celsius. Well, it takes 913 joules to heat 1 kilogram of oxygen 1 degree Celsius. The total mass of the atmosphere would be 980 quadrillion kilograms, so it would take 6.98 times 10 to the 22nd joules to heat it by the desired amount. An object orbiting the Sun at the distance of Mars will be moving at 2.408 times 10 to the 4th meters per second, so 1 ton of material will have a kinetic energy of 290 gigajoules. This means we'd have to hit the Martian atmosphere with 241 billion tons of material to get it to earthly temperatures. The average density of rock is about 2.7 tons per cubic meter. So the total volume of asteroids would be 89.3 billion cubic meters. An asteroid with a radius of 2.77 kilometers would do the trick. This is slightly smaller than the asteroid that killed the non-avian dinosaurs, and this is again assuming we can get it all to burn up in the atmosphere. But once we heat the Martian atmosphere, we have to keep it warm. In order to do this, we'd have to ensure that less of the outgoing infrared radiation emitted by the surface goes back into space, i.e., we'd have to induce a greenhouse effect. The most obvious way to do this would be to put more greenhouse gases into the atmosphere. One way would be to split water vapor into oxygen and hydrogen, and then react the hydrogen with atmospheric carbon dioxide to form methane, which is 64 times as potent a greenhouse gas as CO2. Although, one thing that should be considered when doing this is atmospheric losses due to the solar wind. Because of the lack of a Martian magnetosphere, solar wind particles bombard the upper atmosphere, or ionosphere, and these easily have enough energy to knock a hydrogen atom into space. Meanwhile, very few particles will have enough energy to knock larger atoms like oxygen, nitrogen, and carbon into space. When a molecule gets close to the ionosphere, it will be broken apart or sputtered by radiation, and because oxygen is more electronegative than carbon, the OH bond in a water molecule will be more resistant to sputtering than the CH bond of a methane molecule. This means the higher the methane to water ratio in the atmosphere, the greater the hydrogen loss rate. However, one thing to note is that the solar wind isn't as big of a problem as it's often made out to be. While it did erode the Martian atmosphere to a thin wisp, this likely took hundreds of millions of years, so over the course of millennia, it won't make a noticeable difference on the Martian atmosphere. But if we are worried about what might happen millions of years down the road, instead of using methane, we could produce nitrous oxide from nitrate ores on Mars. This chemical is over 200 times as potent a greenhouse gas as carbon dioxide, and since it doesn't have a hydrogen atom on the molecule, we wouldn't have to worry about hydrogen loss. Going back to the surface, one thing we'd have to do to make the ground more amenable to plant growth is cleaning out the perchlorates. One way this could be done is to grow perchlorate-reducing bacteria in vats and inoculate them in a solution with acetic acid. The acetic acid would be produced by the Fischer-Tropsch reactions that also make the methane. The inoculated solution would be sprayed on Martian soils, and the bacteria would reduce the perchlorates to chloride using the acetic acid as the electron donor. This process could theoretically start on the current Martian surface in equatorial lowland regions such as Valles Marineris, where the temperature regularly rises above freezing and the atmospheric pressure is above the triple point of water. Experimentation has shown that bacteria can metabolize at pressures slightly above the triple point of water. Once we did this, we can take further steps to make the Martian soils more amenable to plant growth. When barren soils are exposed on Earth, pioneering organisms, which are slow-growing but have very minimalistic requirements, will start growing on them. These will then release nutrients into the soil, or at least convert them into a form that's more readily available, allowing less minimalistic and faster-growing organisms to inhabit the soil. Some examples of nutrients made available by pioneers are phosphorus, which is leaked from the rocks, and nitrogen, which is taken from the atmosphere as diatomic nitrogen and released as ammonia. This process repeats, giving rise to increasingly complex and productive communities. Some pioneer organisms that we could seed detoxified Martian soil with are trace gas oxidizers. Organisms which power their metabolism by oxidizing trace quantities of methane, hydrogen, and carbon monoxide, which exist as minor constituents of the atmosphere. Of these, the most abundant in the Martian atmosphere is carbon monoxide at 700 parts per million, which is conversely the least abundant in Earth's atmosphere at 0.1 parts per million. While intuition would state that we'd seed Martian soils with microorganisms which oxidize carbon monoxide, there's a bit of a problem. Because the ambient concentration of carbon monoxide in Earth's atmosphere is so low, organisms which oxidize it do so facultatively, i.e., they can't sustain themselves indefinitely by metabolizing it. So, if we were to seed Martian soil with pioneers, there would likely be microbes we bioengineer. One thing we could do is to give a bacteria with a high radiation tolerance the carbon monoxide dehydrogenase enzyme of a trace gas oxidizer, along with the cytochrome C oxidase, the enzyme which passes electrons to oxygen as the terminal acceptor, from a microaerophilic organism. The reason we'd use a cytochrome C oxidase from this organism is because it would be adapted to metabolize oxygen at low concentrations, and its abundance in the Martian atmosphere is 1300 ppm. We'd also give it a hydrogenase enzyme from a trace gas oxidizer that metabolizes hydrogen. Hydrogen is present in the Martian atmosphere at a concentration of 15 parts per million. The concentration of molecular hydrogen in Earth's atmosphere is 0.5 parts per million. But because the atmospheric pressure of Mars is much lower, the partial pressure of hydrogen there is at most 17 millipascals, while on Earth it's 51 millipascals at sea level. This would make it difficult for any organism to survive on Mars by oxidizing hydrogen. However, what a genetically engineered microorganism could do is use a hydrogenase to strip electrons from a hydrogen, and then use them to reduce atmospheric carbon dioxide to glucose, to in turn be assimilated into their biomass. We'd certainly have to tend to these seeded soils by periodically watering them when the temperature is in the appropriate range. And by appropriate range, I don't just mean above zero, but also not more than a few degrees beyond that point, because with the lower atmospheric pressure, the boiling point of water would be a few degrees above 0 Celsius. But to really accelerate the terraforming of Mars, could we put photosynthetic organisms in the soil? As stated before, plants need oxygen to survive, but this isn't the case for cyanobacteria. However, there is the problem of the intense UV radiation that any organism that could utilize sunlight would be exposed to. The reason photosynthetic organisms on Earth don't get a lethal dose of radiation is because they are shielded by the ozone layer. Ozone itself is produced by photochemical reactions between ultraviolet light and diatomic oxygen. So, does this mean we can't get photosynthesis going on Mars until we can breathe the air? Well, not necessarily. Earth's stable isotope record shows little evidence of UV-induced photochemistry throughout the Proterozoic, indicating an ozone layer was present. But the atmospheric oxygen levels were about 1% of what they are now. This means you would need an oxygen partial pressure of 213 pascals to get an ozone layer. On Mars, it could be even lower, because 1 pascal of gas there corresponds to almost 3 times the total mass of gas overhead than it would on Earth because of the lower gravity. This means we could have sufficient UV shielding once we raise the atmospheric pressure by only 35.5%. Furthermore, once photosynthesis begins on the surface, the excess of organic carbon produced can be used as an electron donor by perchlorate-respiring microorganisms to remove perchlorates from the periphery of the zone where photosynthesis is occurring. This will allow photosynthetic organisms to expand their range and provide more organic carbon in a positive feedback loop. As such, once we increase the atmospheric pressure by adding a little bit of oxygen, a seeded biosphere can begin to expand on its own. Once the atmospheric density is sufficient to start growing plants on unencapsulated parts of Mars, there could be an abundance of nutrients provided by pioneering microorganisms. When the plants die, they will rot and the amino groups in their biomolecules will be released into the soil as ammonia by decomposers. Assuming microorganisms of all kinds will be brought to Mars, some will be nitrifiers, or organisms who power their metabolism by oxidizing ammonia to nitrate using oxygen as the electron acceptor. Should the soils become anoxic, some bacteria known as denitrifiers can use nitrate as a terminal electron acceptor in lieu of oxygen, producing water and diatomic nitrogen. Alternating cycles of nitrification and denitrification can leave some soils depleted in nitrogen. On Earth, the soils are restocked with nitrogen by plants which have diazotrophic symbionts in their roots, which allow them to take diatomic nitrogen out of the atmosphere. One of the major contrasts between the atmosphere of Earth and Mars is that nitrogen constitutes 75% of the air molecules in the former's atmosphere, while only 3% of the latter's. When we adjust for the difference in atmospheric pressure between the planets, the partial pressure of nitrogen in Earth's atmosphere is 76 kilopascals, while on Mars it's, on average, 18 pascals. So far, we've assumed no nitrogen was added, so even though the overall pressure of the Martian atmosphere is greater once terraforming commenced, this number wouldn't change much, only slightly increasing as a result of denitrification. So, could nitrogen-fixing plants get enough to sustain themselves in nitrate-poor soils on the terraformed Mars? Well, to figure out how low the abundance of nitrogen would have to be the limiting factor, we can look at the Redfield ratio. This states for every 106 moles of carbon a primary producer assimilates into its biomass, it will also assimilate 16 moles of nitrogen and 1 mole of phosphorus. The pre-industrial atmospheric concentration of carbon dioxide on Earth is 280 parts per million, or 28.4 pascals. If we divide that number by 106, multiply it by 16, and divide it again by 2, a diatomic nitrogen molecule has 2 nitrogen atoms, while a carbon dioxide molecule only has 1 carbon atom. We get the partial pressure of nitrogen would have to be less than 2.14 pascals to be the limiting nutrient. I say less than because other nutrients such as water, phosphorus, and potassium are usually what limits plant growth versus carbon dioxide. However, the availability of atmospheric nitrogen could still end up limiting plant growth on a terraformed Mars because the nitrogenase, the enzyme which converts diatomic nitrogen to ammonia, possessed by bacteria, may not be able to metabolize it at such low concentrations. Now, as far as I know, no one has done an experiment to see how low concentrations of atmospheric nitrogen impact the growth of nitrogen-fixing plants or their diazotrophic symbionts, and if anyone knows of any, please let me know in the comments. Let's shift gears from the atmosphere to a potential hydrosphere of a terraformed Mars. The total volume of water ice on the Martian surface is estimated to be a little over 5 million cubic kilometers. To put that in perspective, the total volume of the Earth's oceans is 1.37 billion cubic kilometers, while the total volume of Earth's lakes is 113,420 cubic kilometers, with most of that being shared between Lake Baikal, the Laurentian Great Lakes, and the African Rift Valley lakes. Measurements of the Martian magnetic field have indicated that there may be a vast subsurface brine reservoir, and if this is the case, we would have a lot more water available for a terraforming project, but that's still a pretty big if. The total surface area of Earth is 3.5 times that of Mars, so the total volume of water available to make oceans out of is 78 times less when we adjust for the difference in surface area. So, could we make oceans on Mars? Well, the average depth of the world's oceans is 3,682 meters, and if you look at a topographic map of Mars, you can see that there's a vast, flat, low-lying area covering much of the northern hemisphere, known as the Vastas Borealis. The deeper part of this plain covers about 35% of the planet's surface, roughly half that of the portion of Earth covered by the oceans. If we divide 3,682 by 78 and multiply it by 2, we get that if we filled the northern lowlands with water, the resulting ocean would be on average 94 meters deep. This may not seem too deep, but remember that the average depth of the continental shelf, which houses thriving ecosystems here on Earth, is about 60 meters deep. So, the Vastas Borealis could be a vast shallow sea on a terraformed Mars. Although, I should add that there is an additional source of water in the form of hydrated minerals, or minerals that have water molecules in their crystal structure on Mars. It's estimated that the total volume of water in these minerals is enough to cover the planet with between 130 and 260 meters of water. So, if we could add the water in these minerals into the northern ocean of a terraformed Mars, it would be a few hundred meters deep. While this wouldn't make it anywhere near as deep as Earth's oceans, it would be deep enough to give it a dysphotic zone, also known as a twilight zone. This water could be refined out of the hydrated minerals in a manner vaguely similar to the way oxygen would be baked out of rocks to give Mars a thicker atmosphere. However, getting the water out of the crust wouldn't be as straightforward as getting the oxygen. This is because virtually all the rocks on the Martian surface have elemental oxygen in them, so they could be quarried next to an oxygen production plant pretty much anywhere on Mars. Meanwhile, the hydrated minerals are in high abundance only on select parts of the Martian surface. Now, you could argue that since we're designing an ocean, we could chemically make it any way we want, i.e. out of fresh water. But remember, due to the scarcity of nitrogen, we'd probably make an atmosphere with a lower pressure than on Earth, which will increase the evaporation rates. Saline water will evaporate at lower rates than fresh water, so to limit evaporation, it would be a good idea to make the ocean salty. However, the Vastas Borealis isn't the only low-lying area, or even the lowest for that matter. The lowest point on Mars lies in the northwestern part of the Hellas-Planitia impact basin. If we want to make a Martian Great Lake, we could fill the western portion of the Hellas-Planitia basin with water once we remove the salts from the soil. The combination of the higher atmospheric pressure and the lower surface area to volume ratio of a body of water there would make it a suitable place to put a freshwater system. This lake could also act as a reservoir for agriculture in the higher parts of the impact basin. Now, what kind of challenge would people living on Mars face health-wise? Well, with a high radiation present, they will likely have to take iodine supplements and have to shelter underground during solar storms. We might also want to genetically engineer any organism we bring to Mars to have a higher radiation tolerance. While radiation will certainly be a hazard, a big unknown is what impact the Martian gravity will have on human health. It's well documented that living in a zero-G environment has deleterious impacts on human health, but we don't have any idea of what low gravity will do. It might be that we'd start to suffer from harmful effects on Venus with 90% Earth's gravity after a few months, or we could be fine on Mars indefinitely with 34% Earth's gravity. We just don't know. Although, what would be interesting to find out is how high trees can grow on a terraformed Mars. Trees passively move water from their roots to their leaves via capillary action. This means gravity limits how high trees can grow, with the tallest, a sequoia known as Hyperion, being 116 meters tall. So, with Martian gravity, trees grown on it after terraforming could potentially reach 341 meters high. Zooming out and looking at planetary processes, since we keep Mars warm via a greenhouse effect, not only will the average temperature of the planet be greater, the temperature difference between the equatorial and polar regions will be less. This will affect air circulation around the planet. On Earth, there are 3 circulation cells in the northern and southern hemispheres. Near the equator, sunlight heats the air, causing it to rise, and near the poles, it cools, causing it to sink. This means that near the surface, the air will flow towards the equator, and at higher altitudes, it will flow towards the poles. However, the rotation of the Earth causes the airflow to arc east or west to conserve angular momentum. This is known as the Coriolis force, and it results in the airflow emanating from the equator flowing parallel to the latitudinal lines at 30 degrees north and south, while the air flowing away from the poles does so at 60 degrees north and south. As a result, a third circulation cell, known as the Ferrel cells, flows between the Hadley and polar cells. But on a terraformed Mars, the temperature difference between the pole and equator would be comparable to the differences between the equatorial and polar sides of one of the 3 cells on Earth. Also, the radius of Mars is about half that of Earth, and the boundary between the polar and Ferrel cells is half the radius of the Earth. As a result, when the air goes from the Martian pole to the equator, you will experience the change in temperature and angular momentum that air on Earth does when it goes from the pole to the edge of the polar cell. So, Mars would likely only have 1 circulation cell in each hemisphere. Now, how would this affect the climate? Well, as the warm air rises, it cools, causing water vapor to condense into clouds and fall as rain. This means on a terraformed Mars, rain would fall on the northern half of the equatorial regions, as water vapor collected over the northern ocean fell. It would be especially prominent on the eastern side of the Tharsis Plateau, where lateral airflow is pushed up by the increased elevation of the ground, increasing the cooling rate and boosting precipitation rates. This could very well make the eastern part of the Tharsis Plateau the quote-unquote breadbasket of Mars. The rainwater would flow in vast rivers back to the oceans through the Kasai Vallis and Vallis Marinaris, just as it did billions of years ago. Overall, the northern part of the equatorial latitudes would likely be covered in forests. With the circulation cells separated by the equator, very little water vapor from the northern ocean would make it across it, making much of the southern hemisphere resemble a high desert. Think like the southwestern United States. With the area north of the Tharsis Bulge getting less rainfall than the northern equatorial regions, but more than the southern hemisphere, it could end up resembling something like grasslands here on Earth. While terraforming Mars will be a monumental task, we can ultimately turn it into something resembling Earth, but not a carbon copy of it. It will be a monumental and tedious effort that will take global cooperation. But to end on a cliché note, let's make sure we care for our own planet before we start trying to terraform others.